Hi everyone, welcome to our webinar today. The topic for today's webinar is Designing Hybrid Combined Heat and Power Systems, an Introduction to New Features in NREL's REopt Lite tool. This webinar is presented by Clean Energy Group's Resilient Power Project, and we have a number of excellent guest speakers with us today from NREL. Before I pass it over to them, I'd like to go over a few quick housekeeping notes. All of our attendees are in listen-only mode. You have a couple of options to join the audio portion of today's webinar. You can call in using a telephone, or you can connect using your computer mic and speakers. If you'd like to minimize the webinar console so that you can view the presentation full screen, you can click on the orange arrow that you see circled here, and you can also click on that to expand your webinar console. And one of the things that you might like to do with your webinar console is to type in your questions and your comments. We will be saving about 15 minutes or so at the end of the presentation for a Q&A with the audience, and we'll get to as many questions as we can. Do type your questions and comments in as you think of them. A final note, this webinar is being recorded. We will email you with a copy of the webinar recording and a PDF of the webinar slides either today or tomorrow, probably this afternoon. And we'll also be posting all of those webinar materials on our website at cleanegroup.org/webinars. So with that, I'd like to now pass it over to our moderator for today's webinar, Seth Mullendorf. Seth is a Vice President and Project Director here at Clean Energy Group, and he is going to get us started. Seth, over to you.
Thank you so much, Samantha, and thank you everyone for joining us today. We've got a lot of folks on the line, which is great, and we've got some great presenters here today from the National Renewable Energy Laboratory, NREL. Before I introduce them, I'd like to introduce Clean Energy Group to the folks that don't know us as well. Clean Energy Group, we are a nonprofit organization based in Vermont, working across the country. One of our bigger projects is a collaboration with Meridian Institute called the Resilient Power Project. We are almost fully funded by private foundations. You can see a number of our supporters here. And we have a sister organization called Clean Energy States Alliance that is more of a membership organization of groups that manage clean energy funds, mostly state energy offices. So this webinar today is brought to you by our Resilient Power Project, which we've had going for over 8 years now. The Resilient Power Project actually came in the wake of Superstorm Sandy in recognition of the need for more reliable, cleaner backup power sources, particularly for low-income communities, communities of color, and otherwise disadvantaged communities. The goal of that work is to increase access for low-income communities and communities of color to what we call resilient power technologies, which for us mostly means solar PV paired with battery storage on site at community facilities, affordable housing, and other types of buildings that provide essential services to communities during a weather event or other natural disaster or extended outage. We do a lot of analysis in this vein, looking at solar and storage. You can see a number of our reports there, and those are all available at our website at resilient-power.org. We work with folks ranging from small community-based organizations up to city, state, and even federal policymakers to try to get projects developed that support communities. We work as project facilitators in that respect, and also to get policies in place. And our role as project facilitators, we've worked with over 150 projects across the country. I think that's up over 200 projects across the country now, ranging from coast to coast and most places in between. And we help provide technical assistance, usually in pre-development phase of the project, and have a small grant program that can help offset the cost of engaging third-party engineering expertise to do a technical analysis for community services. We mainly work with nonprofit organizations in that respect. So with that, I'd like to introduce our speakers for today, all from NREL, the National Renewable Energy Laboratory. First up, we have Kate Anderson, who leads the modeling and analysis group at NREL. She's program lead for the development of NREL's REopt modeling tool, which we're going to be talking about REopt Lite today. REopt is used to evaluate cost-optimal selection and sizing of behind-the-meter energy assets for grid-connected and off-grid energy systems. Kate's work includes providing technical assistance on energy efficiency and renewable energy technologies to meet energy goals, valuing energy resilience, and evaluating the gap between energy modeling and deployment. Prior to joining NREL, Kate launched satellites as a captain in the U.S. Air Force. Then we have Dan Olis, who is a mechanical engineer with experience in mechanical and systems design, plant operations, testing and commissioning, and project management. Currently, Dan's focus is techno-economic analyses of renewable energy systems, systems integration, and project development. Dan has supported work for the U.S. Department of Defense, Department of Interior, National Park Service, and the Environmental Protection Agency in the continental U.S., Caribbean, and Pacific Islands. Finally, we're going to have a demo of REopt Lite new features from Bill Becker, who focuses on techno-economic analysis of renewable energy integrated with energy storage at buildings and microgrids. His work includes using and developing the REopt tool to perform these evaluations. Bill has experience developing thermal energy storage and high-temperature fuel cell technologies, including the design, build, and testing of pilot plant systems. He has developed energy storage dispatch models for wholesale electricity markets, and he has a broad understanding of power plant and energy storage valuation in deregulated markets. All right, with that, I'm going to turn things over to Kate.
Thank you. Hi, everybody. My name is Kate Anderson. I'm excited to be here today with all of you and to present on the new combined heat and power modeling capabilities. Before I get started, I just wanted to note that Dan, Bill, and I am presenting today on behalf of a large team that developed these new capabilities, which included staff from NREL as well as Colorado School of Mines, the Department of Energy Advanced Manufacturing Office, and the Clean Energy Group. All right, so diving in, REopt Lite is a free, publicly available web tool that's used to guide investment in economic and resilient distributed energy technologies. The first release of the REopt Lite model a couple of years ago, which was funded by the Department of Energy's Federal Energy Management Program, modeled solar PV, wind, and battery storage. This latest release, which is funded by DOE's Advanced Manufacturing Office, integrates combined heat and power to provide a tool for facility owners, industry, to evaluate both the economic and the resilience benefits of hybrid combined heat and power systems that combine CHP, PV, and storage. So when you're trying to think about whether a hybrid CHP system might work for a specific site, there's a lot of different factors that affect whether a system will be technically and economically feasible. Technology costs and incentives, for example, determine the required capital cost investment to install these distributed energy systems. And then these are offset over time by reduced utility energy bills. And the magnitude of those utility bill energy savings is really driven by utility costs and consumption patterns, as well as renewable energy resources and financial parameters. And so there's a lot of these different factors that need to be considered. And so REopt Lite was really created to take into account all of those different factors and concurrently evaluate them to recommend integrated cost-optimal energy solutions. So REopt Lite takes in electric, heating, and cooling loads, which are shown at the bottom of this graph, and then considers a range of different technology options to meet those loads, which are shown on the left here. Technologies are selected by the model considering key drivers, which include economics and goals that the user might have around minimizing costs or meeting resilience or emissions targets. And then the outputs of the model are shown in green on the right, and they include the technology mix and size, the optimal dispatch strategy, and project economics, which include capital costs, operating costs, life cycle cost of energy, and the net present value of the investment. And so on this screen, we've highlighted the new additions to the model that were just released last month in red. And so these include combined heat and power, thermal energy storage, as well as emissions accounting. So I want to talk for a minute about how REopt Lite works. REopt finds the size and the dispatch strategy for this integrated set of technologies to meet the load in every hour determined or entered by the user typically, although the user can constrain the system sizes. But typically, REopt Lite considers the trade-off between the ownership costs of purchasing a technology and the savings that they're going to get across multiple value streams, like on reduced utility bills, to find the optimum technology sizes and the optimum dispatch strategy for each hour. So the example here shows the dispatch strategy for 1 week. And so at the top of this graph, the load is shown in black, and then the utility grid in gray is meeting most of the load. But you'll see that PV is also meeting some of the load during the daytime, and storage is filling in at the end of the day as PV production tails off, but utility rates are still high. So together, solar and storage are able to reduce the peak demand from the grid from about 27 megawatts to about 23 megawatts. And then you can also see that storage is being used for energy arbitrage, which means that it's charging up when utility prices are low and then discharging when they're high. And so REopt is looking for the most cost-effective size and dispatch of technologies to meet the load. Now, it could have built a bigger PV and battery system, but the additional savings would not have been enough to cover the additional costs. And it could have built a smaller PV and battery system, but then the additional savings would have been left on the table. So the model is really trying to find that optimal mix between ownership costs and savings. So this is what the REopt Lite user interface looks like. It's available at the URL listed at the bottom of this slide. REopt Lite can be run in 2 modes, either financial mode or resilience mode. So in financial mode, it's optimizing technology sizes and dispatch strategy to minimize lifecycle cost of energy, like we just talked about. You can also run it in resilience mode, where it's doing the same thing, but it's adding in an additional constraint that the critical load of the site needs to be sustained without any utility power during the grid outage period that's defined by the user. The model is accessible through the web interface, which is shown here, and then also through an application programming interface and open source code. So the application programming interface allows you to script the model to run thousands of different scenarios and sites. So you can look at the viability of distributed energy resources across many sites with different utility rates and renewable energy resources and building load profiles and incentives, or lots of different scenarios. And then the open source code allows you to access all the code behind this model so that you can integrate it into your own tools, or you can take it and change it and add new capabilities and kind of build on it in whatever ways that user needs. And then finally, I just wanted to show an example of some of the key results. I won't go into too much detail because we're going to do a demo, and so you'll see this more later. But just in general, the results include on the left recommendations for technology sizes and the estimated life cycle cost savings. So this is the net present value that you would save if you invested in these technologies. And then on the right, we show an hourly dispatch strategy. So you can see how each of the technologies is operated in each hour of the year. And then on the bottom right, there are some more detailed outputs as well about financial and energy metrics. So at this point, I'm going to pass it off to Dan, who's going to talk a little bit more about the new CHP technologies we've added.
Hi, my name is Dan Olis. I'll be giving a little background on the scope of the combined heat and power model and some description of some key assumptions in our modeling approach. And then I will pass the slides over to Bill Becker, who will give a demonstration of the model. So first, a quick discussion of scope. So as Kate described, we've added combined heat and power to REopt Lite. And so this allows analysis of combined heat and power systems, as well as what we're calling hybrid combined heat and power. So the hybrid in this case includes the other technologies that we've included, which is absorption chillers, thermal energy storage, plus the existing technologies within the REopt Lite tool, which is solar photovoltaics, wind power, and battery energy storage. We think that you'll find that REopt Lite is very useful, that it has capabilities that you'll find useful when you're screening for these, but want to stress that it is a screening tool. It is not a design tool. So experts will need to be consulted before investments are made. However, we think as a screening tool, it'll be useful to you because you can run multiple technologies either individually or together to help identify which of the technologies that you may compete against each other seem to be the apparent winner and which may have synergies where they're complementary from an economic point of view. I want to be clear that there's certain assumptions within the model in terms of what's costed and not. And so this item number 3 here, where we describe it as a retrofit application, is to point out the fact that, which I'll get into a little more on the next slide, is that there's a whole host of infrastructure that we assume the facility has already, and that we're looking at the cost benefit of integrating additional technologies within that facility. So in addition, for the defaults that are included within the model, we're assuming a certain kind of scale that is associated with the cost of the technology as well as their performance. So the model is currently set up with defaults for commercial to small industrial scale. However, this does not mean that somebody couldn't use the model for scales above or below this range. It's just that you'd want to do a careful review of the performance and cost assumptions. I just also want to point out that the technology sizes are typically an output of the model. The user does not need to pick a size of interest. The model does that as part of the optimization. However, a user is welcome to write over that feature and force in a size of interest. So a little more specifics on those assumptions that I mentioned. The graphic at the right is trying to explain that we're assuming there's a kind of an existing facility that has some existing infrastructure that is served by an existing electric service from a utility. If you're going to be screening for combined heat and power, we're assuming that you have fuel already on site, so we're not costing the supply of the fuel. We just have the user input of the cost per unit of fuel. If you're screening for combined heat and power, then we also assume that the facility has an existing central heating plant. And if you want to look at additionally absorption chillers or chilled water thermal energy storage, then we assume also that you have a centralized cooling plant. Baked in within the model is the assumption that the CHP system can operate parallel to these existing systems, so the existing electric utility or the existing centralized heating and cooling plants. It is an hourly model, so we're modeling a typical year, every hour of a typical year, so that's 8,760 hours. And within that period of time, we're assuming that the CHP can serve some, all, or none of the load, whether it be electric or heating loads in any hour. So we don't have any assumed dispatch programmed into there. It's within the optimizations model purview to figure out not only if CHP should be included, but when and how it should operate. I want to be clear too, and this goes back to the point that it's not a design tool. We're not including any redundancy requirements in there or factors of safety, so the model may specify a size that just meets a certain requirement, but it's up to the user and further consultation with experts to refine the model and to refine the results into something that you may want to procure. We're also assuming that, as I said, we're modeling a typical year, but we're doing the economics over a life cycle. So within that approach, we're assuming that the loads at the facility are relatively fixed over the analysis period. So while you model a typical year where we can see how the electricity demand may change, or a solar resource or wind resource may change as a function of time of day or time of year, we are assuming that solar resource, that wind resource, or that load is kind of going to be relatively constant over the analysis period. So we're not looking at, for example, load growth of his facility And lastly, I would just say that if you're screening for combined heat and power, we're assuming that there's room at the facility to install this infrastructure, or if you're adding other technologies, that there's space at the facility to do that. Okay, so lastly, this is my last slide, and then I'll hand it over to Bill. We just want to point out that the model is chock full of a number of defaults for the performance of various technologies. For the combined heat and power, there's 4 prime movers that we model: reciprocating engines, microturbines, combustion turbines, and fuel cells. However, if you go to the model today, you won't see fuel cells in the selection. We're doing some refinement of some of the defaults and costs on this, but it should show up shortly. All these defaults come from the Department of Energy's combined heat and power fact sheets primarily, or were developed in consultation with our colleagues at the Department of Energy. The table at the right shows a set of defaults for the reciprocating engine model, so you can see that there's kind of a range of sizes and costs and performance that vary as a function of size. These performance values are assumed assumed to be correct for kind of iso-like conditions. So I just want to point out that, you know, if you're at a different elevation, we're not making modifications to the performance for that, or we're not making hourly adjustments to performance based on the intake air temperature. So even though we're providing these defaults and we think they're representative, if you're kind of in a unique situation, like perhaps in Denver, where you're at a higher elevation city, it would be important to review some of these defaults. And as part of those defaults, and this is all described in the help manual, which is included online, the heat recovery assumptions are based on certain conditions of the heat recovery fluid. So for water systems, the heat recovery parameters assume that your facility is running 160-degree inlet water with a 20-degree temperature differential across that water loop. And if you're running steam, the default performance parameters assume 150 psig steam. With that background, I'll pass it over to Bill Becker for a live demonstration.
Okay, thanks everyone. Looks like you guys can all see my screen, which is just a browser with Google. So I just wanted to quickly show how quickly it is, how quick it is to get up and running to the REopt web tool. So I'll just type in REopt here, and the first hit should be the link we want to go to. So this is the main REopt webpage on NREL's website, and it kind of shows 2 options here. REopt Lite is the web tool that I'll be giving a demonstration of today. There's also just a link to contact NREL for if the REopt Lite tool doesn't do exactly what you need, you could contact NREL for a more custom analysis. And then there's also some case studies for how REopt was applied to real-world projects. Also some publications and news articles you could read. So then my second click here to the REopt Lite web tool, and so this is the web tool. Up at the top here, it gives you some options to recover some of the data if you've been here before and if you did evaluations in the past and you created an account. So it's kind of suggested that you create an account so that you save all of the data that you, if you did evaluations or uploaded load profiles or electric rate structures, they would be available once you logged back in. There's also some links to a help manual, which is a pretty comprehensive document for for how we represent the technologies, the basis for the default assumptions and the references for those, as well as some more detailed information about just how to use the tool. Yeah, so going down here, this step 0 is just kind of getting you set up, letting you know what you're going to need to do an evaluation. And I talked about this, logging in to access your saved data. Then in the middle here is the data, the minimum required inputs for a financial only analysis. So that's differentiated by a resilience analysis, and I'll talk about that in a second, but there's just a handful of required inputs, and I'll go over those. However, there are probably a couple of hundred total inputs that the users could change. I think we've mentioned that before. You could tailor the analysis to your particular site if you want to tweak those by tweaking those inputs. Additionally, there's a resilience scenario where you specify a grid outage, and then the on-site resources need to provide the power during that outage period. And then so it'll enforce that constraint that it needs to meet that outage, plus it'll do an economic optimization on top of that. So step 1 is just to choose whether it's just the financial optimization or you want to add that resilience component to the analysis. We're going to stick with financial for now. And then we select our technologies. So by default, PV and battery storage are selected, and wind was also available previously, and now we've added CHP, combined heat and power, and chilled water storage. And then if you clicked CHP, there's actually some additional technologies that we've mentioned are available as kind of like sub technologies to CHP. So hot water storage and absorption chiller. There's also a key input of hot water or steam of your existing facilities' thermal needs. So this informs some default performance parameters that are adjusted whether you have hot water or steam. Okay, then step 3 is enter your site data. And so it's your site data, and it's also some economic, emissions, and technology inputs. So it's all the rest of the inputs and fields that you might want to adjust. And there's a handful of required inputs. Like I mentioned, this required text here indicates there's required input fields underneath this tab. So the first one is site and utility. And so at the top, very important, is your location. So I'm just going to choose San Francisco. There's some optional inputs here to give the site a name, land availability. But that location is used for several different things. It's going to load in the local solar resource, wind resource. It's going to load in available utility electric rate structures from the utility rate database that then you can select from one of these. And you can get the rate details by clicking on this link. You can take a look at the rate structure. So I might have a pretty complex time of use demand charge rate structure and energy rate structure in this case. Alternatively, you can put your own electricity rate in, whether it's as simple as an annual blended energy cost and demand cost, or you could do it on a monthly basis, or you could load in your own custom rate tariff that you built through this custom rate builder. And so again, if you have logged in, you could build kind of a detailed rate structure and save it, and then it gets saved to your account. I won't go over that in much detail. So for now, I'm just going to select a utility rate structure that should be applicable to a hospital, which will be the case study I'm going to show. There's some additional inputs, standby charges for CHP, if those are applicable, net metering limits. So that's kind of electrical section. And then since I selected CHP, there's a fuel section. So we need to know information about the existing heating plant as well as the CHP system in terms of the fuel cost in particular. So the two required inputs are just the fuel cost, and for boiler and CHP, those might often be the same. So that rounds out the site and utility tab. And then your load profile is required. That's a key input. So in the case of CHP, we have electric load and heating load. So this one is the electric load. And there's a number of ways you can enter your electric load. One is to leverage the DOE's commercial reference buildings to create a profile that's representative of certain building types. And so I've selected hospital here. You can use the default annual energy consumption, or you could put in your own annual or monthly energy consumption values here, and then it would scale the load profile according to those energy consumption amounts. You can also upload your own 8760 or other interval load data and use that. And then whether you upload it or use your own profile, you can take a look at the hourly load profile here and just get a sense of, on a daily and really hourly basis, how is the load changing. And you can get some summary statistics, average, min, and max loads for the year. And then heating is really the same idea, just with it's the input basis for heating load is the boiler fuel, so the existing facilities fuel consumption. That might be natural gas in many cases, and it's the same idea. You can leverage the reference buildings, or you can upload your own load profile. Okay, so those are the two required inputs, but it's good to see some of the other inputs to get a sense of how the model is using or doing this analysis. So financial inputs, your discount rate is a key input to kind of represent the time value of money in the life cycle cost analysis. And then there's a number of escalation rates that you could use for electricity and fuels, as well as you can adjust the analysis period, kind of the assumption of the useful life of your system. Another thing, so this is the emissions section now. Another thing the location that you entered does is it loads in the default emissions factors for the grid. So it uses the US EPA AVERT database, and it'll select the region applicable to that location to load in that hourly grid emissions factors. And you can, alternatively, you could upload your own values for those. And also here you'd put in your emissions factors for your fuels that will be consuming on site. Then I'll just quickly go over the PV inputs. There's cost, there's incentives, there's tax treatment inputs, and then a number of performance parameters that you could adjust. But there's defaults for all these values, and it's using, also by default, it will be using PV watts to load in PV production profiles based on TMY3 data, but you could alternatively put in your own PV production profile. And then for battery storage, there's just 3 inputs we wanted to highlight: cost, power and energy-based cost of the system. But again, there's a number of other inputs such as replacement costs and performance or sizing limitations that you could put in the model. Finally, down to the combined heat and power section. Like I said, up above, we selected CHP. We could have chose hot water or steam. And then we also put in our load profile, and in particular, our heating load profile. With hot water or steam plus the heating load profile, we're actually coming up with a heuristic size of the CHP system based on the average heating load. This is a common practice for combined heat and power. As an initial cut at the size would be this size based on the average heating load. However, REopt does its own sizing based on the economic value of both the electric production and the heating production of the CHP system. But this is useful to choose a prime mover and a size class based on this heuristic size, so that can inform good default values for cost and performance for all the other parameters. And you could change this if you want. So you can see there's 3 different prime mover types: reciprocating engine, microturbine, and combustion turbine. There will soon be fuel cells as well with the default values for those. And then there's a number of size classes that will modify the cost and performance parameters based on that size class. So there's min and max sizes you can specify. If you wanted to fix the size, you can just put the minimum and maximum equal to the same value. That would fix those sizes, or that size. We do a little cost curve interpolation of cost between the lower and upper bound of that size class, and then we model O&M cost as well. There is, similar to PV and wind, there's the options to put in different incentives and tax treatment parameters. For example, if there might be a local rebate offered by the utility, you could put that in here. And the default federal ITC is 10% that we have loaded in by default there. One aspect of CHP that's kind of unique to CHP is a maintenance schedule. So we know that these CHP systems need to be down for both planned and unplanned maintenance. And we try to capture that by loading in a predetermined kind of maintenance schedule where CHP won't be able to produce. So that might impact, the peak demand charge reduction for certain months, or depending on how it coincides with the load, it'll have different impact. You can view the default unavailable or maintenance schedule profile, some summary metrics of that. Here, you can see it in a different way, the exact periods of time that we're saying a CHP system is down for maintenance. Or you could download this form and re-upload your own custom maintenance schedule. And additionally, there are some more advanced inputs: electric and thermal efficiency, minimum loading, etc., for the CHP system. So assuming I put in all the required inputs, I'll hit go here. And then it brings you to this kind of waiting screen where it's going to give you a status bar saying it's working on it. The model is running. This has been taking between 1 and 2 minutes for PV battery and CHP, a little bit closer to the 1 minute side for this scenario. While you're waiting, you could read some caution text if you haven't been to this screen before. For the sake of time, I'm going to pull up a preloaded results. So this is the screen you'll get to once that completes. And this is the results page. Up at the top, you see the recommended system sizes for all of PV, battery, and combined heat and power. Scrolling down, you have your life cycle cost savings over the analysis period, which is also the net present value. And then scrolling down further is a dispatch chart. It's kind of an interactive dispatch chart, so you can scroll around all 8,760 hours of the year to look at the dispatch, and you can kind of hover over the legend items on the right, and it'll highlight those technologies. But we put the electric grid supplying the load at the bottom in gray to kind of show the reduction in the grid purchases relative to the total load. You could also turn off grid, and it will, this is a stacked chart, so CHP was stacked on top of the grid. If you turn off grid, you can now see how it's dispatching CHP throughout the day. And you can scroll around and look at all hours of the year. We have the same kind of dispatch chart for heating. It's a lot simpler because it's just a boiler and CHP meeting your heating load. So I won't go over that too much. We also have a net load duration curve. This kind of shows how your site load is being reduced for a number of hours throughout the year. You can download all of this dispatch data to a CSV. And then we have a pretty big table. We call it the results comparison table. And what this is doing is it's comparing your business as usual case before you invest in any DER technologies. And then you have your financial optimization case, which we have invested in this case in technologies, and then the difference between those two to kind of do that quick delta there. And I'll just go over kind of the high level sections of what this shows. There's system sizes, there's energy production and fuel use, some additional generation metrics, in particular for CHP, but also like percent renewable energy, emissions section here. And one thing I'll point you to is, I think this is the most useful metric, is the percent of reduction in CO2 emissions from the business as usual case. And then we have year one electricity and fuel costs, life cycle electricity and fuel costs, and then finally some additional financial metrics, such as a breakdown of capital versus O&M cost, payback period, internal rate of return, etc. And then down at the bottom, you can actually download a pro forma spreadsheet, which has all of that data. And I have it here. Has all of that data and more downloadable in a spreadsheet format. And then it also has the cash flow for the life cycle analysis period for both the optimal or financial case and the business as usual case. And this is an interactive spreadsheet, so it has live formulas in the cells. You can get a sense of how it's doing the calculations, and if you needed to modify it at all, you could do that. So scroll back up, I just want to take maybe another minute before we go into questions and answers here. So I wanted to show saved evaluations has, again, all of your previous evaluations you've run, and you can expand this here and kind of see what the details of that evaluation were. You can copy this, which brings you to the inputs page with all of the inputs for that evaluation, and then you could branch off of that and do something a little different. You can go back to the results page, or you could download the PDF report of that evaluation. Additionally, you could select a number of evaluations and compare them, and it'll give you a kind of high-level comparison of the three, or of however many you chose, evaluations. And then, it's good for doing like a sensitivity analysis if you were tweaking an input and seeing how it affected the results. That would be a good way to do that. Let's see. Okay, I think, yeah, we wanted to stop around here so we could answer any questions. I think I covered everything I wanted to. I'll stay on this page.
Okay, great. Thank you for all those presentations. We have a lot of questions to go over, so we will get to those now in the time that we have remaining. Maybe stay over a little bit because I think we're going to struggle to get through them all. Couple of things, high-level questions. There was a question about what's the difference for folks that aren't familiar between just the regular REopt and REopt Lite.
Yeah, I can answer that. So REopt, the regular REopt, is an in-house NREL internal model. It's not available outside NREL. And it includes a wider variety of technologies. Although with this new release, REopt Lite is getting closer and closer to REopt. So I think within the next year or so, we will probably do away with the two different models and just converge on the one REopt Lite model, where we will also be using this for our analyses, and we won't need the internal REopt model anymore.
Very cool. That's great. What question came in? I think you said that this was applicable to small commercial up to large. Can REopt Lite be used or adapted for residential analyses as well?
Yeah, so the one thing that we're missing is a residential building load profile for you to select from. So you can either upload your own residential building load profile if you have it, or you could choose something that seems similar from the commercial building profiles that we have here. So for example, we have like apartment building, but as long as you have some load profile that, appropriately represents a residential building, then everything else can be used for residential.
Great. A question about the energy storage technologies. The default is lithium ion. Is it possible to do other types of energy storage systems or chemistries?
Yeah, so to the extent, oh, go ahead, Bill.
Oh yeah, I just was gonna say, yeah, the default cost and performance is indicative of the lithium ion, but I believe, these parameters could represent other technologies. You just have to bring those inputs to the table and put them in.
Great. A couple of technical software questions. Folks are wondering what the optimization model is that the software uses.
Yeah, we've developed it in-house. It's a mixed integer linear program. So it's looking at both binary and continuous decision variables. The modeling language is in Julia. We call it with the API is a Python-based API, but then it calls this Julia modeling language, which then calls a commercial solver that we use to do the optimization. and all of the source code is available on GitHub. It's completely open sourced. I'm kind of pointing on my screen to where you could get the open source code. And then you can also access the model via an API, which is the same API that this web tool is calling. But if you wanted to interface with the tool that way, you could.
Great. And there was actually some questions about the API, just how it's intended to be used, and does NREL provide any support for API integrations?
Kate, I'll let you answer that.
We have a REopt help desk, and so you're welcome to email us with questions. We don't provide, a lot of support beyond, maybe an hour or two spent answering questions via that help desk, though. There is, though, documentation online that walks you through, how to use the API. It has example scripts. So I think those are good resources for getting started. And then if you run into any issues, you're welcome to email our help desk.
Great. Also a question, go ahead.
Yeah, I was just gonna say that original web tool screen had links to both the documentation for that API, so how you would post, your evaluation inputs to that API and then get results. But then also, if you went to the open source code, there's a whole README section and wiki section for how to get up and running with the open source code itself.
Great. So you mentioned that it usually takes around a minute to run. Does the model ever fail to converge, or take a very long time to converge on an answer?
Yeah, it does sometimes. If you're evaluating all the technologies in particular, that might cause it to run at least close to the max time limit. I think is about 7 minutes before it will time out, and then you'll know, yeah, you've given the model too hard and it didn't solve in that time limit. And then additionally for CHP in particular, if you're modeling part load, variable part load efficiency, that is in particular we found slows the model down. Yep.
Yeah. All right. Some CHP specific questions. There's a question whether there's an option to select renewable biogas as a fuel source or hydrogen instead of natural gas or diesel.
Yeah. So really what that comes down to is just putting in a specific fuel cost representative of that fuel, and also an emissions factor, or emissions appropriate to that fuel. However, we've also mentioned that the cost and performance parameters for CHP are representative of natural gas-based systems, and so there may be variation in performance and cost if you're using a different fuel, and so that again is kind of on the user to customize that. Like if they have a manufacturer's spec sheet for a different fuel or a cost estimate for that different fuel, they would need to put that in there.
Great. Is there a way through the analysis to evaluate the additional resiliency benefit from incorporating CHP?
Yeah, so for a resilience evaluation, what we do is we have the user specify a critical load, whether it's an absolute value of kilowatts for that critical load or a percentage of the total load that you put in. And then, so that's the load that it will have to meet during the specified outage. So it's a specified outage start date and duration. And then, on top of that, so it says you have to meet this outage with our on-site generation, and then it'll do the economic optimization. So if you're considering CHP in that resilience analysis, it's going to show, the value of CHP, versus maybe PV and storage or a backup diesel generator. So it has that baked in I just wanted to describe how, or the kind of the scope of the resilience analysis. We also do like at the end, you can do this kind of statistical analysis for the percentage of outages that it would meet if the outage started any time of the year. That's another kind of statistic on the resilience of that system.
Great. There's a question about the results in the example that you showed, Bill, where it looks like the CHP output goes down to 0 kilowatts on a daily basis. They're just wondering if you could talk about why the tool allows that control scheme, and if there's ability to set a lower operational output threshold for the CHP.
Yeah, so there is an input for the minimum loading for CHP, but it will always allow it to go down to 0. So the idea, or what we have in there now is this minimum electric loading, so percent of rated capacity. So maybe for your reciprocating engine, in this case, it's 50%. So it would never dispatch the CHP system between 0% and 50%. However, there's no way to constrain it to never go to 0%. It always lets it operate or turn off basically in the model.
Great. So there are a couple people that asked if there's been any real-world kind of validation of the results of REopt Lite versus actual install costs in a project. Has there been any validation work that has been done at NREL or by outside sources?
Dan, do you want to speak to that?
Yeah, I'd say the default costs are, the combined heat and power technology itself was integrated with funding from the Department of Energy's Advanced Manufacturing Office. So the costs and performance are supposed to be reflective of real world applications install costs that the Department of Energy Advanced Manufacturing Office recommends that their technical assistance partners use. In terms of the performance of the model itself, the results, we had the technical assistance partners review the model before we did the public beta release. So the validation was done through the careful review of those subject matter experts. We will be doing additional testing of the model with those partners in the future, and then of course look forward to any feedback from our users if issues are identified.
Great. So there were several questions about individual technologies that aren't in REopt Lite, such as heat pumps or solar heating, geothermal. I think just in general, maybe it's the last question is what's next for REopt Lite?
Yeah, so we're in the process of adding geothermal heat pumps to REopt Lite. That's funded by DOE's Geothermal Technologies Office. So we're really excited about that, and I think we will continue to, add new capabilities as we are funded to do so. We would also invite people to use the open source code of REopt Lite and develop capabilities themselves. We'd be really excited to incorporate some of those into the model if the general user community were able to develop things that were broadly useful to other REopt Lite users.
Excellent, and I know you guys are constantly refining the assumptions and some of the inputs and how this works as well. So it's a constantly evolving tool for sure, not just a static one point in time. So I think we're almost out of time here. So thank you very much, Kate, Dan, and Bill. It's been a pleasure having you guys on as always. This is really exciting. And I'm going to turn it back over to Sam to talk about some other webinars that we have coming your way.
Great. Thank you, Seth, and thank you to everyone from NREL. And to everyone who attended today, up on the screen, I've got a list of webinars that we've got coming up, including one that is taking place tomorrow on solar plus storage for Puerto Rico Fire Station Resilience. That should be a really interesting one. We also have 2 webinars next week and then one later in March. They all look really interesting. You can register for those at cleanegroup.org/webinars. So thank you again, everyone, for attending. We hope to see you at some webinars that we have coming up. Bye, everyone.